In 1977, NASA launched the Voyager spacecraft to explore the outer reaches of the solar system. Decades later, both probes have passed the outermost boundary of the solar system, and what they found has amazed scientists. As they entered interstellar space, Voyager 1 and Voyager 2 detected a sudden temperature increase of up to 50,000 Kelvin, a region of hot plasma that marks the boundary of the sun's influence. In this video, we'll explore what Voyager discovered at that boundary, what causes this so-called firewall, and how it's reshaping our understanding of the boundary between our solar system and outer space. Let's get started. When Voyager 1 and 2 left Earth in the late 1970s, they were expected to complete their survey of exoplanets. No one expected that, having achieved their goal, they would continue their journey without a return ticket into the unknown dark region, where the sun's energy wanes and interstellar space begins to speak. Along the way, they quietly recorded the steady decline of the solar wind, the stream of charged particles that is considered the breath of the central star. This was consistent with the decades-old hypothesis that at an unimaginable distance, that stream would collide with the interstellar medium, the thin layer of matter that covers the galaxy, forming the heliosphere, the invisible wall that protects the solar system. The turning point came in 2012, when Voyager 1 unexpectedly crossed this boundary, becoming the first man-made move outside the sun's arms. 6 years later, Voyager 2 repeated the feat, confirming unusual measurements of plasma density and magnetic fields outside the heliosphere. What surprised scientists were the signs that interstellar space was anything but quiet. Higher than expected particle densities, mysterious fluctuations in plasma, and magnetic field variations that didn't seem to fit theoretical models. A series of bizarre hypotheses have emerged. Is there a magnetic membrane surrounding the solar system as a natural shield? Does the interstellar medium contain energy structures we have never seen before? Some researchers have even asked the bold question, could the strange variations in the data be a sign of an unnamed cosmic phenomenon, or worse, a form of noise from an unknown source? While the scientific community scrambles to explain, science enthusiasts are preoccupied with conspiracy theories. Did Voyager really just detect interstellar plasma? Or did it accidentally hit some kind of artificial boundary constructed by an alien civilization? And if there is something unusual outside the heliosphere, are these two tiny spacecraft silent witnesses sending back the first clues to a story larger than the solar system? Voyager continues to hurtle through the endless darkness, its batteries running low, and its signals sometimes only a faint pulse across tens of billions of kilometers. But each packet of data it sends back, however small, carries the potential to shake humanity's perception of the boundaries of its cosmic homeland. The biggest question, to this day, no one dares to confirm, have we really gone beyond the solar system? Or have we just touched the first layer of a door leading to the deep universe with secrets beyond imagination? As they approach the intersection of the solar wind and the interstellar medium, both Voyager 1 and Voyager 2 recorded something that stunned scientists. Plasma temperatures soared from 30,000 to 50,000 Kelvin, 54,000 to 90,000 degrees Fahrenheit, an extraordinary change in a region that was considered nearly empty. The first question was whether the sensors were malfunctioning, but every measurement matched perfectly, forcing researchers to confront a new truth. There was a strange layer of space, a kind of transition zone that had never been clearly described at the edge of the solar system. Rather than a solid wall, like in science fiction, this region is actually a layer of superheated plasma, where the weakening solar wind is compressed by the pressure of interstellar plasma. The collision between these two streams of matter creates a huge shock of energy, enough to heat particles to extremes. Because of its violent and vague nature, like an invisible curtain of fire, the phenomenon has been given a mystical name, firewall of the solar system. Although its name conjures up images of a giant cosmic furnace, the region posed no real threat to Voyager. The plasma density is extremely low, less than 1 particle per cubic centimeter, making it a poor conductor of heat. The spacecraft simply skimmed through this turbulent boundary, leaving behind the first direct measurements from the farthest reaches of the sun's influence. These data confirm that the edge of the solar system is anything but static. Rather, it is a complex, dynamic region where pressure, plasma flow, and magnetic fields twist and turn, creating a natural boundary that separates the familiar world around the Sun from the vast alien interstellar ocean. This chaos immediately raises a number of challenging questions. Why did the temperature rise so suddenly and to such an absurd degree? Is there an undiscovered physical mechanism governing this region? Some scientists theorize that the firewall could be a giant magnetic field surrounding the solar system, acting as a natural energy barrier. More daring theories, often considered fringe, suggest that it could be the remnants of an ancient cosmic structure, a warning barrier created by a long-lost civilization. Voyager crossed that boundary, leaving behind a blazing wall of plasma, a sign that the universe is far more complex than any model humanity has ever built. And the biggest haunting question remains unanswered. Beyond this firewall, how many unknown boundaries lurk in the interstellar sea? Voyager's record-breaking journey turned a once theoretical concept into a measurable reality. The outer edge of the heliosphere, the magnetic bubble that surrounds the entire solar system. Data collected shows that this structure is not only vast, far beyond the orbits of the planets, but also more powerful and complex than previously thought. The heliosphere, a natural shield against harmful cosmic radiation, acts as a defense mechanism for cosmic immune system, constantly reacting to fluctuations from the sun. At the edge of this giant shield, where the solar wind compressed by the interstellar medium, a powerful heating occurs. NASA likens this process to the bow wave of a ship cutting through the water, creating a sudden increase in pressure at the point of contact. Voyager recorded plasma temperatures rising from 30,000 to 50,000 Kelvin, a clear sign of the collision of two winds, the inner solar wind and the outer interstellar wind. Although called fire, this phenomenon is not a chemical combustion, but rather an acceleration and energization of charged particles. These precious data have helped scientists begin to sketch out the true shape of the heliosphere and at the same time raised new mysteries. How can such a massive structure maintain a stable shape in the turbulent plasma of space? Does it oscillate with the sun's 11-year activity cycle? And more importantly, are there undiscovered factors in the interstellar medium that are driving this structure? Some modern theories even suggest that the heliosphere has a self-regulating nature, akin to the behavior of a living organism, its environment to protect its interior. This opens up a bold line of thought. Could the heliosphere be a distinctive energy systems, a signal that other civilizations in the universe could pick up from afar? Even within the cosmology community, there are suggestions that the strange stability of the heliosphere's outer edge could be the remnants of some ancient form of galactic natural engineering, or even the remnants of a civilization that once controlled plasma and magnetic fields at a level unimaginable to modern humans. While mainstream science doesn't support this idea, the heliosphere's outer edge, with its hot plasma and unexplained signals, still feels like humanity is just entering the first door to the universe's many secrets. Thanks to Voyager, the theoretical boundary has become a real space where energy particles collide and create signals that defy all human understanding. And if this is just the outermost layer of the solar shield, then the other side may contain a series of secret layers waiting to be discovered by the next generation of explorers. One of the most striking aspects of the Voyager pair is the distance they have traveled to escape the heliosphere, the region of space dominated by the Sun. Voyager 1 crossed this boundary at 121 astronomical units, while Voyager 2 did so at 119 astronomical units. The seemingly small difference has huge implications. The heliosphere is not a static structure. It contracts and expands like a cosmic lung, inflating when the sun is active and contracting when it is quiet. The boundary surrounding the solar system is thus like a living membrane, a dynamic skin that responds moment by moment to the amount of energy the space. But it was the magnetic data the spacecraft returned that really surprised scientists. For decades, theoretical models predicted that the magnetic field in the heliosphere would tilt sharply from the magnetic field in the outer galaxy. In reality, the magnetic fields were nearly parallel, creating a smooth, continuous transition rather than a sharp dividing line. The discovery forced space physicists to reconsider basic assumptions about how the sun interacts with the interstellar medium. an interaction that may be far more complex than previously thought. These results reveal that the boundary between the Sun's influence and the interstellar sea is not a hard wall or a sharp line. Instead, it is a delicate blend where magnetic fields twist, mingle, and interact. Energy from the two intertwined environments flows back and forth, creating a dynamic intermediate zone that is more complex than previously imagined. And this strange mix opens up a whole new set of questions. Does the transition zone form stable energy flows, magnetic rivers that wind along the boundary between the two worlds? Does the unexpected parallelism of the two magnetic fields hint at a larger structure in the galaxy, an invisible web of magnetic fields that connect star systems? Some bold hypotheses even ask, could the blending zone act as a natural gateway, allowing high-energy particles or undiscovered phenomena to pass through? It was Voyager that helped us recognize that the edge of the solar system is not an absolute cosmic boundary, but a soft and volatile transition zone, where the laws of the sun begin to melt into the broader laws of the galaxy. And it may be that mysterious intersection that holds the key to understanding how the universe enormous scales. Beyond magnetic fields also help reveal how cosmic ray energy particles release events like black holes. The heliosphere acts as a semi-permeable barrier, neither completely blocked nor completely open. Most cosmic rays are deflected by the sun's magnetic field and plasma, but some still get through, depending on how active the sun is at the time. When the sun is active, the solar wind thickens and the heliosphere expands, significantly reducing the amount of cosmic rays that enter. Conversely, when the sun is weak, the shield thins, making the inner space more permeable to energetic particles from deep space. Understanding this process has direct implications for the radiation environment throughout the solar system, from Earth orbit to human voyages into deep space. Understanding the heliosphere's cosmic ray filtering mechanism will not only protect astronauts, but also aid in the planning of future interstellar routes. Projects such as Orion and other ambitious interstellar travel concepts will require this kind of knowledge to ensure human survival in environments where the sun's familiar influence is fading. These findings confirm that the boundary of the solar system is not a static border, but a living, flexible structure, constantly changing with the breath of the sun and the pressure from the invisible energy flows of the galaxy. It is like a thin but flexible skin that covers the solar system, stretching according to the intensity of the sun's anger or peace, and constantly reacting to the pressure of interstellar space. The existence of such a breathing boundary layer raises a big question for science. Does each star system have its own heliosphere with different shapes and characteristics? Can the structure of each heliosphere reveal clues about the possibility of life or the evolutionary history of planetary systems? And more deeply, if humans one day enter interstellar space, will we be able to directly sense the transformation of that boundary like Voyager did? Voyager has demonstrated something important. The solar system does not end with a sharp boundary, but with an energetic boundary where the sun and the galaxy meet. And it is at this dynamic, mysterious boundary that humanity's exploration of the universe may just be beginning. Voyager's passage through the heliosphere was not only a technical feat, but also the first time in human history that a man-made machine had entered interstellar space directly. This was no longer an indirect observation through a telescope or a simulation, but the actual presence of an artificial messenger outside the final protective layer of the sun. The data Voyager collected at this boundary helped scientists build more accurate models of how the solar system interacts with the galaxy, as well as how the heliosphere acts as an invisible shield against the violent radiation that permeates the universe. Understanding the rhythm of this natural shield's expansion and contraction is key to predicting space weather, a vital component in protecting electronics on spacecraft, space stations, and especially astronauts on missions lasting months or years. The heliosphere's rhythmic fluctuations, like the beating of a cosmic heart, directly regulate the radiation levels that future missions will face. Voyager's findings extend far beyond the solar system. In the galaxy, each star creates its own protective layer, similar to the heliosphere, called the asthenosphere, that determines how much radiation reaches the planets in its system. These layers influence the ability of a planet to retain an atmosphere, maintain liquid water, and sustain life. The boundaries now serve as standard data, allowing scientists to model how other stars protect their planetary systems. By understanding how the sun's heliosphere works, researchers can better assess which exoplanets lie in their host star's safe zone, a zone where cosmic rays are sufficiently reduced for life, whether primitive or complex, to develop. Some models, even more boldly, suggest that stars with particularly large or stable heliospheres could form island universes, where life is more likely to thrive than systems with weaker heliospheres. Voyager provided the first direct look at the boundary between the Sun and the galaxy, and from that boundary, the prospect of searching for life beyond Earth became more scientific and feasible than ever. The journey of the two aging probes continues, and each faint signal they send back tells not only the story of our solar system, but also reveals how the universe nurtures or destroys life on worlds we have never visited. Now, both Voyager 1 and Voyager 2 are whispering back fragile signals across vast interstellar distances. NASA engineers carefully manage every last watt of power, essential equipment to maintain the most important sensors. Each signal, as faint as a breath, contains invaluable data on plasma density, magnetic field strength, cosmic rays in interstellar space, regions unexplored by any. These signal strokes on a world no one has ever seen. But the power for these enduring machines is running out. Their radiogenic thermoelectric generators, RTGs, are weakening with each passing year, and by around 2030, Voyager will no longer have enough power to operate even a single instrument. At that point, the two spacecraft that have served for more than half a century will fall silent forever, no longer able to whisper to Earth. But that silence does not mean the end. Though they no longer transmit signals, Voyager will continue its endless journey, drifting among the stars for billions of years, like two fragments of human consciousness silently passing through the Milky Way. What is special is that each Voyager spacecraft carries a golden record, containing sounds, images, and greetings from Earth. It is the sound of children laughing, thunder, ocean waves, wind blowing through trees, and greetings in dozens of languages sent to any intelligence that may find them in the distant future. Those golden records are like messages released into the cosmic ocean, witnessing the existence perhaps more lasting than any construction, any civilization, even the Earth. Voyager's existence has sparked a number of bold hypotheses. Will a distant civilization find them millions or billions of years from now? If so, will they be able to decipher the message engraved on the golden disk? Will they see Voyager as an artifact from a long-lost civilization, or as a greeting from a creature looking for friends in the universe? No one knows the answers, but the very existence of these questions makes Voyager's journey so sacred. Whatever the future holds, the Voyagers have carried humanity's first voice beyond the reach of the sun. They will continue to brilliant but immortal as two cosmic story of the blue planet to anyone lucky enough to listen in the distant future. And even when the light of human civilization has long since faded, those little machines will still be there, carrying Earth's eternal greeting to the entire cosmos. Future missions are being planned to pick up where Voyager left off, extending the exploration of the mysterious interstellar space that the two pioneers pioneered. NASA has proposed a next-generation interstellar probe that would fly 3 times farther than Voyager and carry advanced sensors capable of mapping the entire structure of the heliosphere with unprecedented precision. In addition to surveying the outermost boundary of the Sun's influence, this future probe would analyze the interstellar medium in detail, from the composition of plasma and magnetic fields to the way high-energy particles move between different regions of space. Such missions could answer the big question that Voyager inadvertently posed. Was the super-hot wall they passed through a unique feature of the Sun, or a common phenomenon that occurs around every star in the Milky Way? If every star has a similar energy boundary, it would radically change how we imagine the structure of our galaxy, and could even redraw the map of the interstellar medium in a whole new way. Voyager's findings have proven that the edge of the solar system is not the silent darkness that humans once imagined. It is a superheated boundary, filled with plasma, energy fluctuations, and powerful interactions between two worlds, the inner breath of the sun, the outer endless interstellar sea. What is amazing is that nearly half a century later, Voyager continues to deliver new clues, continuing to extend humanity's reach into a space that was previously only theoretical. At the edge of the solar system, Voyager did not find the absolute void that many had imagined. Instead, it detected the pulse of a living sun, still interacting with the wider cosmos through its own particle streams, magnetic fields, and plasma breath. That boundary was not the end, but the beginning of a larger story, the solar system merging into the galactic sea, and humanity beginning to understand its role in that vast space. Voyager opened the first door. Future missions will cross that threshold, travel farther, look deeper, and perhaps one day explore not only the boundaries of the sun, but also the mysterious workings of the galaxy, where each star may have its own heartbeat, the first echoes of which we have only just heard. If you want to continue to accompany us on our journey to explore the mysterious universe, don't forget to click subscribe to the channel so you don't miss any of the great stories waiting to be told on the other side of the sky. See you soon. Right now, as you're watching this video, our sun just unleashed something incredibly powerful. On December 4, a massive M6. Zero solar flare erupted from its surface. And here's the shocking part, it came from a sunspot that doesn't even exist. NASA satellites captured images in real time, and scientists are scrambling to figure out if this monster is headed straight for Earth. The sun erupted again. Just hours later, on December 4, a newly formed sunspot region known as AR 4300 unleashed a powerful M6. Zero solar flare. It was one of the most significant eruptions from a completely new active region directed at Earth this solar cycle. NASA's Solar Dynamics Observatory captured the flare in real time, recording intense ultraviolet radiation emanating from the sun's southeastern limb. The U.S. Air Force's Space Weather Agency also detected a Type 2 solar radio burst at the exact moment of the flare, indicating a shock wave traveling through the sun's corona. This typically signals that a coronal mass ejection has been launched into space. The NOAA Space Weather Prediction Center is currently analyzing coronagraph images to determine the speed, direction, and likelihood of the CME impacting Earth. This phenomenon is ongoing. What makes this flare particularly remarkable is its mysterious origin. The sunspot region AR 4300 was barely visible until December 2, but just 48 hours later, it suddenly produced an M6, 0 CME. This sudden awakening raises questions about how many other active regions are quietly storing up energy before they burst forth. NOAA is closely monitoring AR 4300 as it moves toward the central disk, a position that could significantly increase the impact of flares on Earth, with solar cycle 25 showing signs of instability. The appearance of AR 4300 underscores the possibility of a more volatile period ahead. Just a few days ago, another X1. 9 flare was also detected from another region, showing an unusual level of excitement from the sun. The M6. 0 event on December 4, clearly recorded by the GOES satellite, carried 60% of the energy of an X1. 0 enough to cause disturbances in near-Earth space. At the same time, the U.S. Air Force detected a Type 2 radio burst, an early sign of a shock wave, and a CME in the making. AR 4300, currently located at S20E45, is gradually rotating into a more direct alignment with Earth. Any eruption from this region over the next 5-7 days has the potential to have a direct impact. Analysis of HMI data on SDO shows a complex magnetic field structure, a feature often associated with powerful eruptions. However, coronagraph data from SOHO and STEREO are needed to accurately determine the speed and direction of the CME. The appearance and intense activity of AR 4300 underscores the limits of space weather forecasting. Each active region sees only about half of the sun's rotation, leaving the remaining 14 days as a shadow where structures can grow unnoticed. This explains why powerful flares often appear shortly after an active region rotates forward. After the December 4 event, debate about the accuracy of the forecast flared up on social media, but experts insisted that the unpredictability of the sun lies not in errors, but in the chaotic magnetic dynamics of the star itself. The fact that AR 4300 flared so just 48 hours after its appearance was not a systematic anomaly, but a testament to the complexity and mystery of the magnetic forces at work deep inside the sun. NOAA's Space Weather Prediction Center issues daily forecasts based on the current characteristics of solar active regions, estimating the probability of C-, M, and X-class flares over the next 24 hours and 3 days. These forecasts are based on magnetic eruption histories of similar configurations, and recent activity trends. By December 3, prior to the M6, 0 event. Forecasters may have raised the overall probability of M-class activity due to the presence of multiple active regions, but with only 1 day of data. It was nearly impossible to predict AR 4300's individual behavior. The controversy surrounding this event once again exposed the difficulty of communicating. Space weather forecasters must balance the need for accuracy with the recognition of inherent uncertainty. Overconfidence in forecasts can lead to complacency, while underestimating satellite systems and the aviation industry unprepared. NOAA opted for probabilistic forecasting, a straightforward approach that acknowledges the limitations of technology but still provides actionable guidance to stakeholders. The M6 zero burst from AR 4300 immediately caused a radio blackout over the illuminated part of the Earth, X-rays and ultraviolet light, which took only about 8 minutes to reach Earth. Heavily ionized the D layer of the ionosphere at altitudes of 60-90 kilometers, causing HF radio waves to be absorbed and attenuated. NOAA recorded an R2 blackout lasting 30-45 minutes, affecting aviation, maritime, and amateur radio communications. But the larger concern quickly turned to CMEs that posed a much longer-term threat than the immediate X-ray burst. If it heads toward Earth, a CME carrying billions of tons of magnetized plasma could create a geomagnetic storm, disrupting power grids, satellites, and navigation. Our Type 2 radio burst was the first evidence of this CME. But to determine its trajectory and speed, to wait for data from SOHO coronagraph, additional views from STEREO. This will help reconstruct the dimensional trajectory. Whether a deflected or a stream of straight for Earth as AR0 approached its impact as of this data being processed to determine the CME was directed directly or completely away from Earth. Given AR 4300's S20E45 position. The CME's initial trajectory was likely tilted eastward, but CMEs typically expand laterally as they propagate. So even off-center eruptions can have a small impact on Earth's magnetosphere. This was the case with the X1. 9 events November 30, which produced a CME that did not hit Earth, demonstrating that each event must be analyzed individually based on its source, location, and spatial structure. The December 4 flare peaked at M6, 0. As determined by the X-ray flux in the 1.8 angstrom range measured by the GOES 1.6 and GOES 1.7 satellites. An M6 0 flare corresponds to a flux of 6 times 10 to the minus 5 watts per meter squared. About 60% of the energy of an X1, 0. The Solar Dynamics Observatory captured detailed images of the flare at multiple ultraviolet wavelengths. The 131 O channel revealed the 10 million degrees Celsius plasma shining brightly at the center of the explosion, while the 171 O channel revealed the cooler coronal ring structure surrounding the eruption region. These data not only confirm the intensity of the event, but also reveal the complexity of the plasma heating mechanism and magnetic activity in the AR4300 region. By analyzing images from SDO and other observing instruments, scientists can determine the magnetic field structure and the energy release mechanism behind the flare. Solar flares occur when magnetic energy accumulated in the corona is rapidly released through a process called magnetic reconnection, where opposing magnetic field lines break and recombine at lower energy configurations, converting the magnetic energy into heat, kinetic energy, and accelerated particles. Electrons and ions are propelled to near light speeds, emitting X-rays and ultraviolet light that fuel the flare. AR4300's magnetic configuration is still being evaluated. Data from December 3-4 show a dipole structure with a densely concentrated magnetic flux over a small area, a sign of a steep magnetic gradient and the potential for strong reconnection. Researchers are looking for signs of magnetic shear where field lines are twisted relative to the field state, and a new increase in magnetic flux extending up through the photosphere, features that suggest the region is accumulating energy to create larger flares. AR4300 is also evolving. Sunspot regions typically expand over several days as magnetic flux continues to rise from beneath the surface. Sunspots are essentially regions where magnetic fields are so concentrated that they inhibit thermal circulation, leaving them colder and darker than their surroundings. Within the dark regions, magnetic field strengths can exceed 3, 0, 0, 0 Gauss, while the quiet surface of the Sun is only a few Gauss. As more flux flows continue to rise, the active region becomes more complex and the potential for eruptions increases. The December 4th flare coincided with the Sun entering the peak activity phase of cycle 25, which began in late 2019 and is expected to peak in late 2024, mid-2025. At the peak, the number of sunspots increases dramatically and flares and CMEs become more frequent. Cycle 25 is considered to be moderate in intensity, not as weak as cycle 24, but not as explosive as cycle 19 inches. The 1,950 seconds, but individual events in any cycle can still have a big impact. The November 30 X1 9 flare is a prime example. This event originated from a different active region and produced a fast CME that was off-axis and did not pose a threat to Earth. The plasma cloud spread out into space, away from the Sun-Earth line, demonstrating that not all high-energy explosions have geomagnetic consequences. Space weather are always closely related to the location of the flare. the direction of the CME, and the position of Earth at the time of the event. Scientists at NOAA's Space Weather Prediction Center are currently running forecast models to estimate when any CME from AR4300 might reach Earth. These models use coronagraph data to determine the initial speed and direction of the CME, then simulate its path as it propagates through the solar wind. The Wang-Xiargay and WSA-Enlil models are two of the standard tools incorporating factors about the background structure of the solar wind and the interactions between multiple CMEs if they occur simultaneously. The travel time of CMEs to Earth varies widely, from 18 hours for ultra-fast events to 0 per second, to 3-4 day CMEs traveling only 300-500 kilometers per second. Based on the intensity of the December 4 flare, it is likely to be a fast CME, although confirmation will depend on coronal imaging. If the CME is partially directed towards Earth, at 200 kilometers per second, it is typical of powerful events. It could reach Earth between December 6 and 8. Forecasters are focusing on two key indicators over the next few days. The first is coronagraph images from SOHO and stereo to confirm the CME and determine its trajectory. The second is real-time data from NASA's ACE spacecraft and NOAA's DSCEV-ARVR, both located at L1, which track the solar wind and provide early warning of an approaching CME. Sudden changes in plasma density, particle velocities, and especially the direction of the intergalactic magnetic field are direct indicating CME. The danger of a CME depends largely on the direction of the magnetic field it carries. If the CME's magnetic field points south, opposite the north direction of Earth's magnetic field, a powerful reconnection process will occur, allowing solar wind energy to flood the magnetosphere and trigger a geomagnetic storm. Conversely, if the CME's magnetic field points north, the storm-causing potential is significantly reduced. NOAA uses the KP and G scales to classify geomagnetic storms, with G1 being mild and G5 being extreme. A fast frontal CME with a strong magnetic component to the south can produce a G3 or even G4 storm. Such events cause voltage fluctuations on the power grid, mistakenly triggering protective equipment, causing currents on power lines, distorting GPS signals, and pushing auroras to lower latitudes, sometimes visible as far north as the United States during G4 events. As AR4300 approaches its maximum impact position, all data from coronagraph and solar wind tracking ships will be crucial to determining whether we are facing a passing CME or a direct impact that could trigger a significant geomagnetic storm in the coming days. These impacts are significant for satellite operators and infrastructure managers. Geomagnetic storms increase atmospheric drag on low orbit satellites, accelerating orbital decay. Spacecraft charging events become more likely. Particles penetrate electronics. Communication systems suffer performance. Airlines to avoid loss of high-frequency communications and increased radiation exposure. Power grid operators implement mitigation procedures to protect transformers from geomagnetically induced currents. This is unprecedented in one sense, the rapid succession of significant solar events. The X1 flare on November 30, and now the new M6, AR4300 on December, erratic behavior maximum phase, while multiple eruptions over several days is not unusual. The involvement of different active regions and the rapid activation of AR4300 show how volatile the current solar environment can be. Scientists are also assessing whether AR0 could produce further eruptions. The region is still visible on the Sun's disk and will continue to rotate toward its optimal position toward Earth over the next week. If the magnetic field configuration continues to evolve, especially if new flux or shear increases, the likelihood of further eruptions remains high. NOAA forecasters will update space weather predictions daily based on ongoing observations of AR4300's magnetic field structure and any activity. Air Force space plays a key role in forecasting solar events that pose a threat to military and infrastructure. Systems such as military communications networks and navigation platforms are sensitive to fluctuations in the magnetic field and radiation emitted by solar events. Therefore, the ability to detect early and accurately analyze the activity is a key element in protecting space security. The Air Force-operated Solar Radio Telescope Network provides continuous monitoring across multiple frequency bands, particularly capable of detecting Type 2 and IV radio bursts, shock wave signatures, CME activity. This data directly complements optical observations from NASA and NOAA spacecraft, creating a dual alert system that provides rapid confirmation of high-energy events. Coronagraph analysts are currently examining SOHO's LASCO C2 and C3 images to measure the CME's angular aperture, speed, and trajectory. Coronagraph C2 observes an area between 2, 5, and 6, while C3 extends to 30 radii. The CME to be tracked expansion phase interplanets appears in these data as structure moving outward. By measuring the position of its leading edge frame by frame, analysts calculate its speed. Comparing its position with background stars helps determine the plasma's three-dimensional. The latest analysis shows AR4300 is a small, sunspot-rich region with a complex magnetic field structure and is potentially active. Ground-based observatories, such as the McMath Pierce Telescope and the National Solar Observatory's GONG network, are using space-based instruments to monitor the region's evolution in real time. The combination of ground-based and satellite observations provides scientists with an independent layer of verification, helping them better characterize AR4300's evolution and assess the risk it may pose in the coming days. Current observations show that solar activity levels remain high compared to the relatively quiet conditions during the recent solar minimum of 2018 to 2019. During that period, days without visible sunspots were quite common. In contrast, December 2024 will see multiple solar activity regions appear simultaneously on the visible disk of the Sun. This increased activity is expected to continue through 2025 and into 2026 as solar cycle 25 approaches its maximum phase. Scientists are looking to a broader range of space weather monitoring capabilities. The solar observation fleet includes NASA's Solar Dynamics Observatory in geostationary orbit, which provides continuous high-resolution imaging. The Solar and Heliospheric Observatory at the L1 Lagrange point provides coronal and heliosysmic instruments. The twin stereo spacecraft, one now retired, provides off-axis imaging of the Sun. Ground-based observatories around the world contribute optical, radio, and magnetic field measurements. This network of observing platforms allows for comprehensive space weather monitoring, but there are still many shortcomings. The dark side of the sun cannot be observed directly except through helioseismology, which provides limited information. The time between a CME launch and its arrival on Earth allows forecasters hours to days of advance warning. But accurately predicting the intensity of geomagnetic storms remains a challenge because a key parameter, the CME's magnetic field direction, cannot be measured until the plasma cloud reaches upstream monitoring spacecraft, just 30 to 60 minutes before impact with Earth. Summary: the December 4 eruption of AR 4300 highlights the dynamic nature of and the inherent challenges of space weather forecasting. The region emerged, grew, and produced a significant flare in a short period of time, limiting forecasters' ability to provide early warning. This pattern is typical of solar active regions, which can evolve rapidly and unpredictably. The question now is whether this CME will impact Earth and what the potential impacts will be. If coronagraph analysis confirms an Earth-bound trajectory, NOAA will issue a CME warning and monitor geomagnetic storms. Satellite operators will review spacecraft health management procedures. Power grid operators will prepare to mitigate geomagnetically induced power line impacts. Airlines will monitor space weather updates to inform polar flight routing decisions. Radio operators and Aurora Watch prepare for possible at high latitude. Over the next 40 hours, aircraft data and propagation find the casting community clear answer potential impact. December 4 CM. The demonstrates that forecasting tools the sun retains to surprise. Active regions appear on timescales, the ability to continue to work weather models, their observation, and improve the physical processes that drive solar eruptions. Each major event, like the M6, zero flare from AR 4300, provides data that helps advance this effort. As of December 4, the sun remains highly active and unpredictable. Numerous sunspot regions are present. The potential for solar flares remains high, and the possibility of additional CMEs remains, as long as complex active regions remain in the solar disk facing Earth. What's happening right now at M6, zero flare from sunspot region 4000, 300, a type 2 radio burst that suggests a possible CME, and ongoing analysis to determine the potential impact on Earth, reflecting the reality of space weather in the solar cycle. If you want to stay up to date on the latest solar events, CMEs, geomagnetic storms, and ongoing scientific analysis, be sure to subscribe so you don't miss any important developments. Leave a comment with your opinion. Is AR 4300 just the beginning of a larger chain of events in solar cycle 25? Right now, as you watch this video, North America is tearing itself apart. The Rio Grande Rift beneath New Mexico and Colorado is pulling our continent apart at a rate of 1 to 2 millimeters per year. That may sound small, but it represents geologic forces so enormous that they could eventually split our continent in two and create a new ocean. This isn't science fiction or far-fetched speculation. GPS satellites are measuring this continental rift in real time. Seismometers record the tiny earthquakes that mark each microscopic tear. Volcanic fields dot the landscape, where molten rock rushes through ever-widening cracks. The truth is, North America is already in the early stages of a continental breakup that began 25 million years ago. What happens next depends on forces at work deep beneath our feet. The Rio Grande Fault system stretches more than 1,000 kilometers from central Colorado through New Mexico and into Mexico. To understand what this means, imagine a crack in the Earth's crust longer than the distance from New York to Atlanta, and it's getting wider. This massive geological feature began forming 25 to 35 million years ago, when the tectonic forces acting on North America changed dramatically. The continent compressed for millions of years, then began to expand. The crust stretched like taffy, creating the deep valleys and mountain ranges we see today. Current GPS measurements confirm that the rift is expanding at a rate of 1 to 2 millimeters per year. To put that in perspective, your fingernail grows about 3 millimeters per year. The entire North American continent is being stretched at about 2/3 the rate at which your fingernail grows. This seemingly small number represents a huge geological force acting over vast distances. The action of the rifts becomes clear only when you know what you're looking for. It was the silent stretching of the Earth's crust that created the Rio Grande tectonic plates pulled apart, and the central block slid down the fault, creating a deep valley carved out over millions of years. Repeated ruptures laid down vast sedimentary basins, like the evolutionary diary of the continent. Layer by layer, volcanic activity in the region continues to expose the power of this system. The Jemez Range, Valles Crater, and young lava fields are remnants of magma seeping up through weaknesses in the crust. They are still smoldering, evidenced by hot springs and geothermal gases. Clear signs of molten rock moving beneath. Some scientists even believe this could be the early stages of a new rift system forming. Earthquakes here are the steady vibration activity, though most are too small to be felt. Seismometers register dozens of tremors each month, each a tiny adjustment as the continent continues to expand. The quakes are concentrated along major fault zones, like the Earth's deep heartbeat. Modern INSAR technology reveals subtle deformations on the surface. The Rio Grande Rift is still moving, leaving behind measurable signals despite the seemingly peaceful landscape. In fact, the Earth is operating under powerful and unpredictable forces beneath its fragile crust. This rift system reshaped the entire southwestern United States, creating the characteristic topography of the basin and range region with its wide valleys and long mountain ranges like giant folds. This was a direct result of extension causing the basins to lower and the mountains to rise. What makes the Rio Grande special is that, in contrast to many other continental faults that have cooled, it is still active. The conditions that shaped it over 25 million years seem to have remained intact, like a long tectonic experiment that humans have only happened to witness. The East African Rift is a perfect analogy there. Rifting has created the Red Sea and the Gulf of Aden as young, expanding oceans. The Rio Grande may be at the beginning of the same path, raising the question of whether tens of millions of years from now, North America will be split in two by a new ocean. Though this scenario is far-fetched, it casts a shadow over the current landscape, as if a major geological restructuring has quietly begun. Scientists often describe continental rifting as a three-act play, each one scribbling on the fate of a landmass. In Act 1, the Earth's crust begins to experience almost invisible tensile forces. But over time, These simmering stresses weave into the first network of faults, fissures as thin as cracks in glass, heralding a quiet geological transformation. Act 2 opens with the formation of deep valleys as blocks of crust are pulled down, and young volcanoes emerge, awakening magma pushing through the weakened crust to create entirely new landscapes. In Act 3, the last continental plate finally separates, the gap between them gradually filling with nascent oceanic crust, marking the birth of a young ocean at the heart of the planet. The Rio Grande Rift is now in the midst of Act 2, a position both fascinating and fragile. It has advanced far enough to form deep valleys, young volcanoes, and clear signs of surface deformation, but it has not yet reached the point of full separation. Geologically, the prospect of it becoming an ocean in the distant future, perhaps tens of millions of years from now, is not unreasonable. Yet the process is anything but certain. Earth's history is littered with unfinished faults, spreading systems that were started but never completed, stuck forever in a state of midlife. These aborted tectonic projects are still imprinted in the landscape today, whispering stories of the Earth's crust's incomplete journeys. It's this uncertainty that makes the Rio Grande one of the most closely watched rift systems in North America. Scientists wonder if we're witnessing the first spurts of a nascent ocean within the continent, or just the edges of a rift that will cool and fade into oblivion. Every tremor, every layer of cooling lava, every millimeter of movement detected by satellites could be a crucial piece of the puzzle. The region has become a giant natural laboratory where the Earth is quietly testing the forces that will shape its own destiny. Continental rifts have been going on for ages beyond human imagination. But the Rio Grande Rift's current place in this evolutionary cycle reveals something remarkable about the geological future of North America. Watching the Rio Grande is like following a chapter in a book still in progress, where each new discovery could change how we envision the fate of an entire continent. Act 1 of rifting begins with a gentle but persistent expansion of the Earth's crust. Tectonic forces deep within the planet silently push continental plates apart. And from these barely perceptible movements emerge a primitive fault network. This is a period that can last tens of millions of years, during which the crust thins and weakens, preparing for more violent changes. For the Rio Grande, this phase is gone. The fault formed during that period is the tectonic skeleton that clearly defines the present-day rift zone boundary. The fact that the Rio Grande has completed the first phase of its tectonic journey and is moving into a more active phase makes the question of its future more intriguing than ever. Is the entire system quietly moving toward a transformation that will reshape the map of North America in the distant future? Or will it stall mid-course? Like so many other failed fault zones in Earth's history, new geological data, every millimeter of surface deformation, every trace of old magma is like a piece in a giant puzzle that scientists are still patiently piecing together. It's this uncertainty that makes the Rio Grande not just a subject of study, but a geological mystery waiting to be solved. Stage 2 ushered in a period when the landscape began to change dramatically. Deep valleys emerged, volcanic activity increased, and the continental crust continued to stretch, becoming thinner and weaker. This is the state the Rio Grande Rift is experiencing today. As the forces of extension continued, blocks of crust collapsed between major fault zones, creating deep basins that span several states in the southwestern United States. At the same time, The weakened crust opened up natural channels for magma to rise, giving rise to numerous young volcanic fields, vivid signs of the Earth's constant movement just beneath its quiet surface. One of the most reliable signals that the rift zone had progressed into stage 2 was the emergence of a type of volcanism typically seen in oceanic environments. In contrast to the silica-rich eruptions of continental environments, where the thick, viscous, explosive magma of rift systems began to shift to a thinner mafic composition similar to the basalt flows that erupt from mid-ocean ridges. This change in magma composition was a subtle but significant signal that thinned enough that magma backed directly with the flow, altering the nature of the eruptions. Remarkably, some volcanic Rio Grande rift zone show exactly this kind of chemical shift. They are silent beacons that the system is moving closer to stage 3, the point at which the continents may completely separate and new oceanic crust begins to form. Is this a prelude to a future proto-ocean, or just a fleeting moment in a tectonic system that will eventually stop? Each rock sample, each ancient eruption, each chemical trace analyzed is like a secret sign that the Rio Grande leaves scientists, stirring curiosity about its true fate. Stage 3 marks a crucial moment. The continent doesn't just stretch. It actually breaks apart as the crust gets too thin. Molten rock from the mantle rises and crystallizes into new oceanic crust right in the Rift Valley. If this process continues long enough, ocean water will rush in, initially stagnating in troughs, then gradually expanding into a narrow band along the rift. Over enough geologic time, that sea could expand, much as the Atlantic Ocean did when the supercontinent broke apart some 200 million years ago. The movements that created the ancient ocean may be quietly replaying beneath our feet. Only the Earth's rhythm is too slow for humans to perceive. If the Rio Grande Rift continues on its current trajectory, an inland sea could one day extend from central Colorado all the way down to the Gulf of Mexico. While this scenario may seem far-fetched, it fits perfectly with modern tectonic models. Initially, the sea would likely be just a narrow band a few kilometers wide, snaking through the Rift Valley. But over millions of years, as new oceanic crust is continually carved out along the fault, the sea would widen and deepen, eventually becoming a true ocean basin. The emergence of volcanic islands would be another important signal that a new ocean is forming. As magma from the mantle rises through the young ocean crust, it can accumulate into chains of submarine volcanoes. Some may rise above the sea, forming new islands. These islands may be violent at first, then stabilize as the fault system settles into balance. The scenario calls to mind Iceland, a country perched right on the mid-Atlantic ridge, a vivid example of a young ocean creating new land. The Rio Grande's potential as a starting point for a future ocean makes the system far more than a geological structure. It becomes a window into the distant destiny of the entire North American continent. What's most fascinating is that all this movement is happening right now, silently, slowly but steadily, to the deep pulse of our planet. The fate of the Rio Grande Rift depends on whether the tectonic forces that are pulling it apart persist. If those forces weaken, the system could stall, like many ancient rifts that never complete continental separation. But if they sustain or strengthen, the prospect of North America being torn apart along the Rio Grande is entirely possible. GPS, seismic, and volcanic data show that the rift is clearly still active. It widens steadily each year. Tremors occur constantly, and magma persists below the surface. But the slow rate of seismic activity leaves much uncertainty about the system's future. The impact of rifting is not just a matter of study. It directly affects the lives of millions of people. Cities like Albuquerque and Santa Fe sit directly on the rift zone, facing the risk of earthquakes, deformation, and possibly future volcanic activity. Regional planning must therefore be based on a long-term perspective as the continent silently changes. Understanding the Rio Grande's evolutionary trajectory is key to how communities prepare for and adapt to natural disruptions. It's a collaboration between science and human resilience, as tectonic forces are constantly at work beneath our feet. The Rio Grande is just one part of a vast tectonic network that shapes the entire western part of North America. Parallel fault systems interact like cogs in a giant geodynamic machine. The Basin and Range Province, one of the most dynamic extensional regions, is where the crust is stretched into dozens of parallel valleys and mountain ranges like giant folds. GPS measurements show that the area is expanding at the same rate as the Rio Grande, just a few millimeters a year, but never stopping. Accumulating over 17 million years, it would double the entire area. This proves that the seemingly static landscape of the American West is actually constantly shifting, following the Earth's slow breathing, from the Rio Grande to the Basin and Range. The entire network raises a big question. Is Western North America entering the early stages of a major continental breakup? Every geological record, however small, reveals a future that may be far beyond our imagination. The San Andreas Fault system does not exist in isolation, as many people imagine. It is directly connected to the vast extensional network that stretches across the Gulf of California. In fact, this famous strike-slip fault system is just one part of a larger continental rift. Baja California is slowly but steadily separating from mainland Mexico, while new oceanic crust is forming at the bottom of the Gulf of California. This is a vivid demonstration of the deep interconnectedness of the Northwest American plate. The movement of the Pacific plate northward relative to the North American plate not only creates the San Andreas Fault, but also stretches the entire region from the Rio Grande to the Basin and Ranges. As if the continental margin were being pushed northwestward, modern seismic activity across the region is an echo of deep tectonic processes. California's 2019 Ridgecrest earthquake, Utah's 2020 Magna earthquake, and the myriad small tremors that keep hitting New Mexico are not random events. They are the inevitable result of the Earth's crust deforming in real time. These tremors, along with the silent shifts recorded by modern instruments, show that the North American continent is constantly changing shape, albeit too slowly for humans to feel directly. Geothermal features tell a similar story of powerful energy building beneath the surface. Hot springs that stretch across the western United States, from the geothermal steam plumes of Yellowstone, through the scattered hot springs of Nevada, to the thermal fields of New Mexico, indicate that the crust has thinned and is being heated by magma rising near the surface. They are natural windows into the deep world, where tectonic forces continue to fuel continental transformation. Modern monitoring technology has pushed human observation to entirely new heights. INSAR satellite interferometers can detect ground movements as small as a few millimeters over hundreds of kilometers. Seismic networks record thousands of small earthquakes each year, vibrations that were completely invisible just a generation ago. Millimeter resolution GPS stations allow scientists to track the slow movement of tectonic plates as if they were watching the Earth itself breathe. These data highlight an important fact. Earthquake preparedness in the western United States must take into account the diffuse nature of extensional tectonics. Unlike the San Andreas system, a prominent and easily identifiable extensional fault can have a much more complex and unpredictable pattern. Building codes, urban planning, and emergency plans must therefore consider this diffuse seismic hazard as a central, unavoidable factor. The Earth, in its dynamic nature, is constantly reshaping the landscape around us through processes both subtle and powerful. Continental rifts are symbols of the planet's most powerful geologic forces, forces that operate over millions of years, slowly but inexorably. The Rio Grande Rift and its associated extensional systems are clear evidence that the future of North America depends on forces at work right under our feet. These changes manifest themselves in measurable ground movements, in seismic activity, in volcanic systems that continue to influence modern human life. And so, the journey to explore the mysteries of the Earth, from tectonic cracks to forming oceans, will open up many more wonders. See you again in the next journeys into the dynamic world of the blue planet, and don't forget to subscribe to the channel to continue watching. See you again.